Okay, I know this is the last obstacle before the very well-deserved coffee break, so I'll try to be quick and I'll try to keep you awake, if I can. So we know that case-based planning can fruitfully exploit the knowledge gained by solving a large number of planning problems, but in order to be effective, it needs to be able to identify similar reuse candidates. It is, to some extent, like playing Guess Who, if you know the game, and I hope you know the game. So basically, you have a target problem, which is the guy over here, and you are checking your case base, which are all the other guys in the back, for identify similar reuse candidates. It should be noted that in the case of planning, the case base is a bit larger, but not so much. And this step, which is called plan retrieval, as I said, is of critical importance for the case-based planning process because it strongly affects the ability of the planner to solve or not a given problem. And what are we doing in this paper? We are basically describing an innovative technique which is based on planning features. And in particular, we observe that the existing set of features, the existing largest set of features, is not always effective. Therefore, we introduce a new class of planning features and we demonstrate their effectiveness. Now, let me just go quickly through the case-based planning process. So the first step is the plan retrieval, which is the one on which we are focusing on today. The idea is that you got a target problem, you check your case base, and you identify problems which are similar. From these problems, you take the plans and you evaluate them in order to identify the single plan that you will then adapt to solve your target problem. And the fourth step is plan revision, in which you are actually testing, basically, that the adapted plan is really solving your target problem. And finally, you can store the new couple problem plan into your case base. And here we have basically an overview of the case-based process in which all the interactions between the process and the case base are highlighted. The plan retrieval step is critical and it must be at the same time efficient and effective. Efficient because for every new target problem, you have to check all your case base in order to identify the similar ones. And effective because clearly you want to identify those which are really good to reuse their plan for solving your actual problem. And so the first experiment that we did was to test and to reuse the largest set of features which have been proposed for planning, which have been introduced last year in the last ICAPS by Fawcett et al., and which include 311 features that are extracted by considering different aspects of planning, like different encodings, such plus or SAT, by extracting some pre-processing statistics of some planners, by analyzing the search space topology by using Torchlight, and also by considering probing features, where probing features are basically information that you can extract by short runs of planners. Basically, you take a planner, you run it for 1 second or 2 seconds, and you extract all the information that you can from its trajectory. And what are the problems that we observed in these, when using this set of features? Well, we identified 2 main issues. The first one is that their computation is extremely expensive, up to tens of minutes. That's because the case-based planning is fruitfully and is, let's say, can be betterly exploited when the problems are large and complex, clearly. Otherwise, the classical generative approach can perform better. But this issue can be overcome, clearly, by selecting a subset of these 311 features. But the second issue cannot be overcome, and it is that basically they are not always able to distinguish between problems, which means that given 2 problems, all the 311 features has exactly the same value, although you know that the 2 problems are different. So basically, going back to our Guess Who example, you are going from the game to the left to the game to the right, which is a bit harder to solve. And here we have an example of one of these indistinguishable problems in the logistics domain. So here the goal is to have all the packages in airport 2, and in the upper side, we have a description of the initial state of one problem, and in the lower side of a different problem, which are, according to the use of this Fawcett feature, indistinguishable, although you can see that they are quite different. So what we did, well, we introduced a new set of planning features, and for doing so, we consider the planning encoding graph. What is a planning encoding graph? Well, it's a graph that you generate given a planning problem. So let's go through this example in Bloxworth. First of all, you generate one node per each object of a problem, in this case A, B, C, and then you consider in turn the goal description and the initial description. Let's start by the goal description. Here we have two predicates, on AB and on BC. For each predicate, you generate one node, which is G on, where G clearly stands for goal, and you connect this new node with the involved objects. So on AB means that you connect G on with A and then A with B, and on BC means that you connect G on with B and then B with C. And these sort of connections are identified by the labels. And you can do basically the same with the initial state. In this case, we have 4 different predicates. We generate one node for each one, and then we connect again with all the objects. For each problem, 3 different of these graphs are considered. The complete graph, which is this one, the basically graph which describes the relations of the goal, which is only the upper part, and then the one which describes the relation of the initial state, which is the lower part. And from these 3 graphs, we consider 2 different versions, the directed version and the undirected version. So basically, you are considering or not the direction of the arcs. And we extracted features from which describe the size, the degree, the size and the presence of strongly connecting components, and in general, the structure of a directed graph. And from the undirected, again, size, degree, components, which are basically the correspondent of strongly connecting components for undirected graph, the number of triangles, and the transitivity. We consider size and degree for both directed and undirected, because in the undirected version, you are basically losing some sort of information, because clearly, if you have 2 nodes in the directed graph, which are connected from one to the other and from the other to the first one, in the undirected version, you have just one arc between them, without any direction. So, considering the planning and coding graph and considering the 2 directed and undirected graph, we extract a total of 115 features, where 19 plus 18 comes from each peg. Then we consider the sequence of vertex degrees, which are called degree sequences usually in case-based planning. And for free, because we use LPG for generating these pegs, we consider also the number of instantiated action, fact, and mutex relations. Now, given this new set of features, how can you use them for evaluate the similarity of planning problems? Well, a planning problem is described by a sequence of features, and given 2 problems, so the target problem that you want to solve, and 1 problem from your case base that you are analyzing, you compare all the couple of features, and you evaluate their normalized difference. And then the similarity between the 2 problems is basically 1 minus the average of these differences. So this basically means that a similarity value of 1 means that according to your features, the 2 problems are exactly the same. A similarity value which is closer to 0 means that they are extremely different. So it is very unlikely that you will use the plan of the 1 problem for solving the other one. And then in your case base, you order the problems according to the similarity value. And you will select the top of them for going through the plan evaluation step. And in order to evaluate our approach, we tested it using 6 domains from IPC. For each of them, we generated a library of 6,000 cases, a library which is organized in clusters, where clusters are basically set of quite similar problems that range from 34, which are the smaller in rovers, and 107 for the Xeno travel domain. How do you generate these clusters? Well, you select some problems which are either large-size competition or randomly generated using the available random generators. And the problem in a cell cluster are basically generated by changing at most 10% of the literal or by adding and deleting objects from the problem. Given these 6,000 cases, we have all the solution plans which were generated by using TLPlan, and the plan length in general is between 72 and 519 actions. For each domain, you then consider 25 test problems, which are derived by those which are in the case base, and you basically change part of the initial of the goal factor, again, you add or remove objects. Why are you doing this in this way? Because it gives you some sort of, let's say, very high level validation of approach. So you know if you are testing one test problem which came from the cluster A, very likely the most similar problem will come again from the same cluster. So from this level, you can have some sort of validation of your approach. And we consider the state-of-the-art case-based planner, OAKPlan, and we gave it half an hour and 4 gigabytes of RAM. And here we have an overview of the results. So in the first line, we have OAKPlan, which is exploiting its original plan retrieval approach, which is based on kernel function. Then OAKPlan exploiting our new approach with all the features, then only features from the complete peg, from the goal, and from the initial state. And what we can basically see is that using the proposed approach significantly speed up both the overall planning process, which is described in the speed score, which is basically the IPC speed score for the process, and the plan retrieval step, as it is highlighted here, where the matching time is the average matching time in CPU seconds. And basically, we have a couple of order of magnitude here. And in terms of quality, we are basically very close to the original approach. And here we have a different perspective of the results in which we are showing the CPU time for the whole planning process of our approach, which is the blue line, and the original OAKPlan exploiting kernel feature, which is the red line, on the domain in which we perform best, which is rover, and the domain in which we perform worse, which is logistics. And as you can see, even in logistics, in general, our approach is better, although sometimes the original one is slightly faster. And then we compared, again, OAKPlan using the original function and OAKPlan using our feature-based approach with classical generative approaches like FF, Llama, LPG, and SGPlan, and also against them in terms of CPU time, OAKPlan exploiting these features is faster. In terms of quality, again, it is very close to the original OAKPlan, and also LPG performs pretty well. So what can we say? In conclusion, case-based planning is extremely useful in real-world application in which the topology of solved problems does not vary much. But the critical step is to deal with plan retrieval. And so what we did in this work, we proposed an efficient feature-based approach, and we observe that the filtering process is performed quickly, and that the proposed method can significantly speed up the state-of-the-art case-based planner, OAKPlan. Now, at this point, you can say, okay, Mauro, you have shown us something which works well in case-based, but who cares about case-based planning? So let's see what are the potential applications of an efficient and effective similarity function. Well, we have found basically two of them. The first one, which is assessing the usefulness of training sets. So usually, in learning for planning, what are you doing is you generate a set of training problem. You train, basically, so you extract knowledge offline from this problem, and then you run it online. But if a training set includes problems which are too similar, this might lead to overfitting, for instance, and this is something that you can avoid by checking their similarity. And on the other hand, you can also measure the representativeness of the training problems with regards to the testing one. So you can understand if the knowledge that you are extracting is worthy to be used, or it is too far away from the problem that you want to solve, and so it is probably better to stop and extract new knowledge, or just evolve the knowledge that you are using. And speaking about the future work, we are clearly interested in investigating these two areas, and we are also interested in analyzing different functions for evaluating the similarity value of the two problems. So far, we are basically using the Euclidean distance, and also identifying important features within the considered set, and also considering the fact that very likely important features will be different from domain to domain. And that's all. Thank you.